A few principles. So what we're going to do is we're going to focus on a few principles, and in particular, some that I really like. So catalysis is one of them. It's a really interesting element in the green principles. And, there's been lots of books written about it, even talking about catalysis, the key element of green chemistry or other similar things, because catalysis is really amazing because it will tackle a bunch of other green principles. So if you do catalysis, you often reduce waste, you improve efficiency, you improve your energy usage, you improve things on a lot of grounds. So you touch at least 4 or 5 other green principles as you do this. So again, catalysis, you remember, guys, this is when you add an additive to the reaction in a non-stoichiometric, so less than stoichiometric condition, and it's going to drive the reaction forward. Catalysis is among the most relevant cultural human accomplishment in the history of mankind. It's comparable perhaps to agriculture or the wheel or cars or the internet, which is Benjamin List, the Nobel Prize in 2021, said that. We consider that approximately 80% of the processes in the chemical industry requires the use of a catalyst, and directly or indirectly. And we think that catalysis contributes to 25% of the global GDP. I really like this quote from Emil Fischer, who more than 100 years ago saw all the potential that catalysis would have up to today, saying the chemistry of gases has come for some years now has for some years now entered a new era, that of catalysis. And this is again more than 100 years ago. With the aid of catalysts, now succeed the most wondrous transformations by hydrogen, oxygen, nitrogen, carbon monoxide at temperatures many hundreds of degrees lower than one previously saw these gases react. This chapter of catalysis is almost unlimited. And I think that we're seeing green chemistry being empowered by this technique because of this, the fact that it is indeed an unlimited area of exploration. So what is happening here? When you do chemical transformations, what you need to do is to deliver energy to your system. And this energy is used to do something that we call pass the barrier of activation. So essentially, this is the same thing as when you have to go home by walking, and you know that you have to go over a little hill. So you live your work and you're like, oh, I have to go back home, and I'm gonna have to go up that hill, and it's gonna cost me a lot of effort, right? But you have to do it because you have to go back home, so you do it. But what catalysis does for you is that it's providing a little tunnel in between the hill so that you can actually go home without climbing as much. And it's doing that because it's providing some reaction pathway that is actually lower in energy than the one you need with the classic non-catalyzed reaction. So this is how it works. So the way it works, and we saw that earlier, is that catalysis works in a cycle. So this means that your catalyst initially being free to react will interact with the starting materials, make the transformation happen, and then release the product here while being recovered in an unaffected way. So what's really important is that the catalyst after the cycle is identical to the catalyst before the cycle. This is essential so that the catalyst can run that multiple cycles, essentially. The reaction from the starting materials to the product can, in theory, be accomplished an infinite number of times. So your catalyst here, you can imagine that it's going to go over and over and over. Of course, this is not always the case, and there are cases when your catalyst is actually going to break apart. Oh, sorry, my this is an example where we're comparing here catalyst with a stoichiometric reagent. My apologies. So here you have reagent A that is going to interact with starting materials A and B to combine them together and form the product that you want. But after the reaction, your initial reagent is completely discarded and thus you generate a lot of waste, right? So with catalysis, so this is an example of a reaction that can do that. So this is sodium boral hydride used as the reducing agent. the reaction is happening, and at the end of the process, you recover BH3 or sort of degradation molecules from this guy, as well as sodium hydroxide. So you see, you generate waste here right away from the fact that you have used a stoichiometric reaction. Instead, if you use catalysis, what you do is you find a way to loop this back, so somehow recover what is waste now back into your reagent, and now you make a catalyst, and you reduce the number of waste because you need to add a lot less reagent in order for the reaction to proceed. This is how you can directly impact the quantity of waste. So again, catalysts are ideally eternal, but I want to say that over time, stuff happens and your reaction and your catalyst may break down. And when it does, what we do is we calculate the number of cycles that the catalyst went through. And that's going to be a measure of the performance of the catalyst. Of course, the more cycle your catalyst can do, the better it is, right? Makes sense. So what we say is a catalyst can be defined by its turnover number, TON, which is the number of cycles that it can go through. And you can also calculate something called turnover frequency, which is the number of cycles divided by time. So a really efficient catalyst is one that will go through multiple cycles. And a really fast catalyst is one that will go through lots of cycles as a function of time. So you can compare catalysts this way. What you want to do too is you have a catalyst that is going to give you only one product, the product you want, hopefully, and not many. So this is where we talk as well about selectivity. Selectivity is another measure of the quality of a catalyst. So these are some ideas around some of the things you can do. So metals are been used a lot as catalysts in a number of different setups. They suffer from having lower turnover frequency as compared to enzymes, which are truly excellent. They also have a selectivity that is not as good, but they tend to be used a lot because they're often cheaper than using enzymes, and especially entertaining the enzymes in a good environment is something that's a little bit challenging to do at times. But these are some of the really highly performant catalysts that people are using for these types of transformations. So just to give you an idea of what catalysts look like, here are some examples of catalysts that are out there. Zeolite, this is a crystalline material, crystalline aluminosilicate, which is used in a number of applications, and it's a central catalyst that is used in petrochemistry in particular. You have metal catalysts deposited onto surfaces, which are used again in a number of applications, from petrochemistry to more commodity chemicals. Enzymes or biocatalysts are used really a lot as well. This is really an area in development these days. And we see more and more chemical processes being performed by enzymes. You also have homogeneous catalysts like acids or for instance here, just classic acids, Bronsted acids. This is one of the most common catalysts actually that is used out there. A number of reactions are catalyzed just by changing a little bit the pH in one direction or the other. This is an example of an organocatalyst, L-proline, which is used because it provides an N2 selectivity when you make your catalyst, which is really interesting. This is an example of a metal complex that is used for especially reduction reactions, and it's also having some enantiomeric activity to make asymmetric molecules. So we can classify them as biocatalysts, heterogeneous catalysts, which means that we can separate them very easily from the reaction medium, versus homogeneous catalysts, which are solubilized, so we cannot easily separate them from the reaction medium, but they often tend to be a little bit more efficient and fast. So biocatalysis in particular is super interesting. In fact, we've been using human beings biocatalysis for a really long time. Think about the manufacturing of bread, for instance, which is happened by enzymes that are able to generate CO2 from sugars, or wine. Winemaking is actually a biocatalyzed reaction. You can think about so this is how it was made initially, but now we are developing new catalysts by using bioengineering techniques, such as here using recombinants, and that allows us to now make catalysts to do amazing things like chemical transformations that we would never anticipate them to do initially. Some of the ways you can do that is by doing directed evolution, which is a way that you can make biocatalysts, make enzymes, and then mutate them, and cycle after cycle take the best mutants to get eventually super active biocatalysts for new functionality. So this is really something that is developed really rapidly and is being actually now enhanced and implemented by robotics as well as artificial intelligence. So we're going to see more and more development in the biocatalysis world, and probably more applications as well to this area. These are some examples of homogeneous organocatalysts that are used out there, and in particular using organocatalyst as a potential catalyst for transformations. Metal is still used a lot in this area, especially, for instance, for petrochemistries, for commodity chemicals transformations. And there's been a lot of research lately to try to, so initially a lot of metals are taken in this rarest metal area because they're very, very active for a number of transformations. For instance, rhodium, palladium, ruthenium, excellent hydrogenation catalysts, for instance. And now research is really focusing on trying to replace them with these guys, especially iron or titanium or copper, which are much more common and thus will be much cheaper to develop. So this is an area that's really rapidly growing these days. An example of a catalyst that we all use in our cars is the catalytic converter. So this is something that has been implemented in an effort to reduce the production, to avoid the production of a number of noxious gases from the combustion engine in our cars. So with a catalytic converter, what you can do is you can take molecules such as CO that can come from the combustion of fuels, hydrocarbons that are not completely burnt, and also nitrous oxides, which are really noxious because they cause acidic rain. So this is what's coming out of your engine, and what you want to do is you want to make sure that you get rid of these guys. And you can do that by using a catalytic converter. So inside your car, you have this big pocket here that contains these matrices onto which you have little tiny particles of platinum. And what the platinum does is that it is actually completing the combustion of CO all the way to CO2. So of course, we don't like CO2, but we prefer much better CO2 to CO because CO is really toxic. So we don't want to have that in the environment. What you can do is also complete the combustion of other unburnt hydrocarbons so that you will completely burn it. Again, here what you want to do is you want to avoid the production of small hydrocarbons that can cause aerosols and also be much more harmful greenhouse gases in and of themselves. And finally, you want to reduce the NOxes here using CO as your reducer so that you will avoid the production of nitric acid in the environment, which causes acidic rain. So this is the implementation of these catalytic converters, despite the fact they use platinum, which is really expensive, has been a really big advancement so that we lower the pollution caused by transportation. Catalysis is really well known because it is providing an environment that will allow to achieve this other green principle called atom economy. So you remember what we say in atom economy is that we want as many atoms we put in the process to end up in the product. And one big example of that is when you're doing a transformation that is enantioselective. So it means when we introduce inside our material a chiral environment. And usually when you do this reaction, if you do this transformation from here to there, and you do not have something that will control the center, you will form two enantiomers, the one that is like this and the other guy that is that has this particular functionality on the front. And when you do that, you don't have good atomic economy because you need to throw away half of this. So one of the first things that people have been doing is develop some transformations in which you use here, in this case, a catalyst, which is a rhodium-based catalyst, which is chiral, so that you will favor the formation of that center here. An even better system is actually using a biocatalyst, where you will do this transformation as well, and also introduce your chiral center. And you can compare here the performance in terms of selectivity. You see that you get a better system this way, and thus you will have better atomic economy overall and less waste. So this is by performing these transformations so that you favor one enantiomer over the other with high efficiency. Another example of how catalysis is very good is relationship to efficiency, energy efficiency in particular. So in this particular transformation, you have you're trying to make these funky looking molecules here. So again, I'm not trying, I know that we have a number of people in the audience who are not chemists, so I'm not going to detail here the chemistries, but you can see here these funny looking molecules. In this particular transformation, initially, you need to work just want to make sure I don't yeah, in this particular transformation here, I'm just going to compare here these two transformations. This one here, you work at minus 78 degrees, which actually requires a lot of energy to provide. So when you compare with this new method, so from the glass close mix line to the Sumitomo chemical method, you see that in this transformation, they make the same molecule, but without having to resort to these low temperatures, and that's actually very energy efficient. So that's an example of how you can really get better system, and they can do that by using an appropriate catalyst. In this case, they use this proline-based organocatalyst as compared here to using a metal-based pi box catalyst. So another example as well is catalysis can help you with degradation. So one of the big problems we have with permanent molecules that don't degrade, is actually plastics. We all know that if we throw plastics in the environment, most of them are not degradable and they're going to stick around. But catalysis can offer us a solution to that problem, and especially biocatalysis. So this is an example of how people have engineered different enzymes that they're called PETAs, or in this case, so PETAs, or in this case, MHETAs, which are a range of enzymes that have the ability to break down PET. Again, PET, remember, this is the polymer that is used for all the water bottles that you have. This one, you can break it down using this enzyme and then break it down even further to the initial starting materials using a second enzyme here. And by engineering the enzymes, you can actually make very highly performant systems that are able to break down plastics. And this is what it looks like. So you see here the surface of your plastic with no enzyme. Here, the surface of your plastic with a wild type PETA. So this is one that they collected from nature. You can see that it's forming these holes in the plastic, which means that the plastic starts to be degraded. And then this is the mutant that they've developed, which is much more active, and you can see it's digging even further holes inside the plastics, hence showing that it can degrade it. So what you can see from there is that by looking at this catalysis green principle, we have the ability to reduce derivatives, design for energy efficiency, have atom economy, pollution prevention, and design for degradation that is integrated in just this one principle. So there's lots of connections between them. And, and we could have like played even more with Lars to build more connections, right? But this is just to give you the power of this wheel here, where we have a lot of connections between the different principles. The second thing that I wanted to talk about as well is the notion of solvent. Solvent is really ubiquitous around us. And for those of you who are working more in the formulation area, solvents are also really important. Solvents will facilitate reactions. They're used for everything from extractions to dry cleaning to paints to formulation and much more. But the use of toxic solvents really affects people directly, as well as the environment. So again, it will be really, really difficult to identify something around us that has not touched solvents at any point of its life. And we have, for instance, again, the material that we have on our tables. It's a great example of something that has been made in an organic solvent. So these are the examples of where solvents are used. So in fabrication, they used to facilitate the meeting of molecules with one another. So this is what we use them. They're a mediator. They're also really important for mediating the temperature inside the reaction. So to deliver thermal energy to the molecules, as well as take away thermal energy that's generated during chemical processes. So it's really important, very important role that solvents play there. In the processing, they allow us to manipulate chemical product, but they're not an integral part of the molecule itself, right? We also use them for extraction and separation. We can separate and purify chemicals based on how they interact with the solvent, for instance, being more or less soluble in one solvent versus the other. We also use them in cleaning to eliminate oil, grease, oil and grease, for instance, and silica from chemical parts. This is a big use of solvents, actually. And finally, formulation, where we design a product on a process that will be delivered in a way that is really appropriate by the mixing of the active ingredients with solvents. Cosmetic is a big example of where formulation matters. Detergents, another one. Paints is another one, where again the solvent serves here a very critical part. Where there's a problem is that solvents, like chemicals, can lead to hazard and thus risks. So you have the fact that your solvent can have inherent toxicity. So methylene chloride, chloroform, and other halogenated solvents are suspected human carcinogens. So this is something that you would like to reduce. They can cause inflammation as well. They could be flammable. My apologies. Which means that they will catch fires really easily. You can actually know their properties by looking at the flash point. The flash point is the ability for a solvent to self-ignite. So it's a temperature that will give you an idea of how flammable and imminently flammable the solvent is. The lower the temperature of the flash point, the more dangerous the solvent is. So check it out. And a solvent itself might be flammable and entertain a fire if it catches fire. Explosivity is a potentiality that it will explode. And if it's used in large volumes, of course, it could be absolutely disastrous. There's also global warming potential, reduce the ozone layer. That's happening by reducing the ozone layer. So we know that fluorinated compounds in particular have this ability. And then the reuse of solvents is really important, because if it's not reused, of course, it will be a major source of waste that will accumulate as well. So these are some of the pictograms that you have to identify some of these issues. You recognize here toxicity, flammability, and explosivity. So JSK, but also other companies have produced different solvent selection guides. So I mentioned another version of that earlier today, but this is another one that you can see here, where you have lists of different solvents related to their toxicity or flammability or explosivity. And the ones that are in the red here are the ones who have one or several of these bad output out there. So for instance, chloroform is really bad. It is toxic. Benzene is toxic as well. So it's going to be placed here. There's also ether that is going to be there. Diethyl ether is here because it's highly flammable. It has a low flash point and so on and so forth. This is the use of the solvents in industry. You can see that it's used a lot in paints and coatings, so definitely something really important. In pharmaceutical, it's present there because it is used a lot in the synthesis of the molecules. You can see here cosmetic being also really important, as well as household care. So definitely really ubiquitous in a lot of different industries. An example here is in the composition of a typical paint. You can see here that in volume, the solvents occupy the majority of the actual product that you're selling. So it's really major, actually, the consideration that you have to make for the solvents. This is what when you make a water-based pen, for instance, it's really obvious how it puts you in a much better situation right away. So alternatives would be using water or sometimes solvent-free systems. So powder coating, for instance, is a technological solution. Again, thinking outside the box, right? You could make coatings via powder, which helps you prevent the generation and the use of so much solvents. So in industry, you would use solvents in particular for making molecules, again, as a reaction media. This is a story from a famous molecule, sildenafil, which is also known as Viagra. The conventional synthesis, including 11 steps, and the total yield was only 4.2%. And it used more than 1,300 liters of waste in order to produce it, 1 kilogram of the product. But with an alternative production, we've been able to reduce it to only 3 steps with 97% performance, and now we can have only 7 liters per kilogram that is used of solvent. So this is an example of how green chemistry really helps you very much for this. And I can tell you, these are processes that have been implemented because pharma company, they really see a big incentive in doing that. So that's an example of successful implementation of a new route. And yeah, this is how this is happening. So this is kind of a timeline over time about the discovery on this molecule and how it started at this 1,300 liter per kilogram at the medicinal chemistry stage, and how it became, after again several works and sort of green chemistry principles being applied, it goes to 7 liter per kilogram. Sorry, this is the commercial rate that is currently done. It does have a solvent recovery process, which is some of the reason why you can really lower this to that level. And they have future target reducing it even more. Another thing that's really interesting is that if you look at the makeup of the solvent that they're using here, you can see that it used to use a lot DCM, which is a really, really nasty solvent. And now there's almost a very, very tiny amount of DCM here. Most of the solvents are actually much cleaner ones, such as methanol or 2-butanone and ethyl acetate as well. So green alternatives to solvents is also trying to avoid solvent altogether. And this is something that we discussed already a little bit yesterday through the use of mechanochemistry. So when we use mechanochemistry, you can actually do this transformation without any solvent. This is an example of a polymerization reaction that is done by ball milling without any solvent being used. Another alternative is to use a benign system, such as water, as a better system, or supercritical fluids that have been used, or also reduce the volatility, which is another problem of solvents, via developing ionic liquids. So we're going to look a little bit into these examples in the next few slides and see what we can derive from them. So water, for instance, has been developed as a really interesting solvent for different transformations. This is two examples actually of transformations that have been improved drastically by using water. And they were actually, it was really interesting because these are processes where when you change them for water, not only do you use less of the toxic chemical, but also you increase the yield. So this is really two very interesting examples that you can use in teaching in particular for that application. One of the So water is really good. We saw an example yesterday of water being a very good solvent, but not being good enough, actually. So this is really interesting. In organic transformation, water is really nice, but there are some limitations. And one of them is that when your reagents are all hydrophilic, you may have issues having reactivities. Some reagents are not very reactive in water. So you have systems that may or may not work. And for this reason, people have developed what's called micellar chemistry. So this is the use of surfactants in water, which allow to create a nano environment here where you can actually do transformations that are happening in more lipophilic environment while still using the bulk of your solvent as being water. So that's a really beautiful work by Bruce Lipschitz at University of Santa Barbara, and he's been developing some of these really nice surfactants here, which have proven to be really nice for promoting water as a solvent and at the same time enabling reactivity that you could not do in water typically. Supercritical CO2. This is a really interesting solvent as well that is actually commercial for from one interesting application, which is the decaffeination of coffee. So I know that here you guys grow coffee, right? So I don't know if you have a decaffeination process here in Indonesia. Who said yes? Do you have decaffeination here? No, okay. So anyway, the way that this is done is that you're taking your coffee beans and you're going to remove caffeine from it. So this is an extraction process. And initially it's a reaction that you would do using some pretty toxic solvents, such as benzene or dichloromethane. But an alternative to that is using supercritical CO2. So the way this is done is that you can take your green coffee beans and you can soak them in water and then use supercritical CO2 as a way to extract the caffeine. And what's really cool about that is that at the end of the process, so this is the way it works here, they're soaked in water so that they really expand and they can be extracted easily. You will inject in there supercritical carbon dioxide. So this is carbon dioxide that is not really liquid, but looks like very fluidy. And as it's going through the beans here, it's going to entrain solely caffeine. And then at the end of the process, you depressurize your CO2. It becomes a gas again. And all the caffeine can bubble through here and go into water. And you make caffeinated water. And you can send that and you can sell it to Coca-Cola so that they put it in their drinks, or you can sell it to you could just remove the water and sell it as caffeine powder for whatever application you want. So this is really, really interesting process that people have been using. And this is an example for extraction, but you can do chemistry as well inside supercritical CO2, and people have been developing that. So that's a little infographic. Sorry. That's a little infographic about the chemistry of decaffeinated coffee. You recognize here the caffeine molecule, which is similar to the theobromine molecule that I have around my neck, by the way. Some people have asked. The initial processes has been using some methylene chloride or ethyl acetate as the extracting agent, which is really nasty. I mentioned the decaffeination by CO2. You also have a process called Swiss water process, which proceeds via water only for removing caffeine and flavor compounds from coffee. Another example is using deep eutectic solvents and ionic liquids. So these are a specific kind of reagents that are working on, these are specific kinds of reagents that are liquid despite having very high charges. So these are salts, right? You have a positive charge and a negative charge. And what you know usually of salts is that they're solid in regular conditions, right? The salt table that we all have on our tables, this is a solid that we use to sprinkle on our food. But ionic liquids are salts that have some interesting properties to be liquid at room temperature or at least below 100 degrees. And these molecules are really interesting because although they are liquid, they have a very, very small vapor pressure. So what this means is that they're not going to be volatile very easily, thus they're not flammable, and that makes them very safe to use. You can make them from, so this is the ionic liquid. This is what I would call the first generation of these. Generation is called DES, deep eutectic solvent, which are going to be acting as liquids via an hydrogen bond interaction between a donor and an acceptor. And these are really safe alternatives. They're usually non-toxic and they're made from biomass. So EDS is really a big field these days. And finally, I'll just give you one example of how you could use liquids and change their properties over time by simply doing some smart design. So this is an example of a molecule here that could change its property from being ionic or non-ionic simply by bubbling CO2 inside. And what this means is that now you have and you can go back and forth bubbling CO2 or N2. And what you can do with that is you can make, for instance, a transformation in a lipophilic environment, then change the properties of the solvent. All your products are going down because they're no longer soluble in this environment. You remove the solvent, you can put it back here and start the reaction again. So this is a great way to extract solvents and reuse them in a way that will save a lot of waste generation. And finally, I want to spend a bit of time on the solvent-less reactivity, which I think is really interesting. So this is when you are using solid-state mixing or ball milling or mechanochemistry, reactions happen. So typically, you could do that by using bowls that are going to be used here for mixing solid states. You can or vibrational or planetary mills. And you can do a bunch of transformations. So for instance, Suzuki cross-coupling, Sonogashira, or azide alkyne cycloadditions can be done in this way. So this is just to show you the versatility of the chemistries. I could have given you, 100 examples. Now you can, a lot of named reactions have been developed by mechanochemistry, let's put it this way. Mechanochemistry is based on some of these tools here. So we could use mortar and pestle, planetary mills, we mentioned that, the vibrational mills. There are more modern versions as speed mixing, resonant acoustic mixing. And we discussed aging as well yesterday as being important as well, to do transformations in a solid phase while not actually putting any chemistry. Another cool system, putting any mechanical action, sorry. Another cool system is extrusion, which is a form of mechanochemistry that happens in flow. So you can add reagents here, have your product come out here. The transformation happens via shearing inside this screw extruder. And that's something that is being used a lot in pharma, for instance. It's being developed a lot in pharma. So we actually, I don't know if I showed that to you yesterday. I don't know if you guys can click on this or not. At the bottom here, if you, yeah, so this is the way a vibrational mill works. So you can see here a bowl going back and forth and forming these H shapes inside the reactor here, and really acting here as a mixer for the powder that would be inside. That's the way mechanochemistry works. And that's the way we're doing a lot of our transformations in our lab. So very briefly, I wanted to give you a few ideas about how mechanochemistry works. Because it's a little bit mysterious, right? You can take reactions in a solvent, and now I'm telling you, well, you can get rid of the solvent, it's going to work the same way. It's not quite that evident, but a lot of transformations can definitely be transformed into mechanochemical ones. So what's important in mechanochemistry is you start with a solid state reagent, and what the first thing you need to do is to make sure you break them down into smaller pieces to have a high surface area so that the reaction can happen at the interface of different grains. So initially, what mechanochemistry does, it reduces the grain size and it increases the surface over volume ratio. As it's doing that, it also helps reagent mix intimately with one another so that you start to create interfaces where two reagents can meet and start reacting with one another. Another important aspect is what we call mechanical activation. So it's using this power of mechanochemistry to make transformation happen. One of the main mechanisms is something called deformation. So as you take a molecule and you act on it by putting pressure on it, you modify the bonds inside the molecule and you lower the activation energy for the transformation. This is an example for cellulose here that in a ball mill can be bent. And when it's bent, it has a much higher reactivity than when it is straight. So that explains that this particular bond breaking here, which normally happens at close to 200 degrees in cellulose, now in the ball mill happens at 30, 40 degrees. So it's really massive help to do mechanochemistry because it really helps with activating the molecules to make them more reactive at lower temperature. Another mechanism is one that we call the hotspot model. It's one where this is for really much harsher mechanochemistry, I would say, when you really bang you really bang balls together with a lot of force. You can create locally hotspots that have the properties of plasma and can create really high energy conditions for some difficult transformations. This can be used for transformations such as here, the transformation of calcium carbonate into calcium oxide. So much harsher chemistries, but nonetheless also something you can do with mechanochemistry. And finally, you can have different additives. So in mechanochemistry, we can use liquids, we can use salts that are going to help with reactivity. And this is just an example from the formation of co-crystal where we change the different additives, we change the quantity of these additives, and we have different outcomes as we play around with this, really showcasing that there's a lot of versatility in this process. And finally, aging, I mentioned it a few times already. It's another form of solid state reactivity you can combine with mechanochemistry. Typically, you will mechanically activate a powder, reagents in a powder form together, and then you let them age over time. And this is what it looks like in my lab, where we have powders that are aging inside Tupperwares, where we can control conditions of temperature and also humidity. And that allows us to track reactions as they evolve. So mechanochemistry is also something that has been linked to green chemistry in a number of ways. If you want to read more about this, there's been a paper just written about that. And the reason why it helps with green chemistry is that by lowering the quantity of solvent that you use during the reaction, but also often during the separation and purification, you end up with a process that results in less solvent use, so less waste, but also can lower the energy activation and also can allow us to work with safer chemicals. So all of that really taps onto many principles of green chemistry that we mentioned earlier. Again, like everything that I mentioned, mechanochemistry needs to be evaluated by proper metrics. So I just wanted to place that slide here, but this applies to anything I'm talking about. all of the benefits that we're talking about when we say we're going to replace the solvent, we're going to remove the solvent, we're going to add a catalyst, we need to really come out with good metrics each time to prove that it's better chemistry. And we do it now. You could use the process mass intensity, you can use the LCA, you choose what you want. Of course, you have to justify why you make that choice. But finding a good metrics to explain what you do is so sometimes people will publish papers in mechanochemistry and say, oh, mechanochemistry is known to reduce solvents, hence it's good. That's not enough, because you need to justify why you use this method specifically for this problem, and also explain if the reagents are as safe, for instance, as the one you use in liquid state. So that's an example of really something important. So again, like earlier, we have been talking about safer solvents and auxiliary, and demonstrated that by having safer solvents, we tap onto less hazardous chemical synthesis, pollution prevention, accident prevention, as well as catalysis. All of these are impacted by the choice of safer solvents. I just want to make sure that how we're doing in terms of time.
Okay, so maybe 5 more minutes, and then we go to the Q&A session. Yeah.
Final, yeah, great. So maybe I'll finish with the renewable feedstock. So another important, very important point in the green principle is the renewable feedstock. So the advantage of using renewable resources is obviously it's obvious and crucial for a way of life. If we switch to renewable feedstock and renewable energy, we're going to get to a world that is more on a sustainable trajectory. Again, this is related to the fact that you want to move out of fossil resources because that generates direct impact on climate change. So this is the slide that you've seen before. What we want to do is take our products from biomass as opposed to taking it from petro resources, because this allows us to circulate CO2. So that's the basic principle of why we want to do this. It is really difficult, though, because right now petrochemistry is really everywhere. So in terms of energy, it is still 80% of all the energy production around the world. It stays. It's really depressing to me because I've been teaching green chemistry for almost 20 years, and every year I renew my slide and it's always at 80%, because although renewable energy is going up, it doesn't account for the growth. It only accounts for the growth. So it remains at an 80% value. This is just crazy. But if we focus on chemicals alone, there's also a lot of things that petrochemistry does for us. So if I look at a barrel of crude oil, for instance, you can see here that based on it, you can extract 27 crayons, some 1 quart of motor oil, which is lubricants. You can make some charcoal briquettes. You can also generate electricity, which can be used for lighting your lamp here. You're also going to make propane, the equivalent of 12 small cylinders. You will make asphalts, the equivalent of a gallon. You will make gasoline to power your car for about 280 miles. And also you can make distillate fuel that will be used for larger trucks. But in addition to that, you will also make a bunch of stuff, like some plastic stuff, for instance, toothbrush, pocket combs, drinking cups, plastic telephones, polyester shirts, plastic dustband, hula hoops, and so on and so forth. So really showing you that you can make a lot of stuff. And what's not even drawn here is all the chemicals you will make, including drugs, detergents, and so on and so forth. If you think at biomass, you have a lot of things to play with. You have, of course, plants, which is the majority of where we can look into for chemicals, but also animals. So we've seen yesterday the examples from crustacean shells of what we can use, where we can use biomass. Fungi is another big place. Bacteria is another one that people are trying to develop. So there's lots of things that you can do, and this has led to a number of development of mushroom leather in an effort to try to replace the use of leather from animals. You can make fuels from algae, which is a really interesting mechanisms for generating biofuel. And you can make plant-based plastics. We're gonna talk a bit more about that actually. So some of the interesting molecules for biomass is, for instance, the ligno. So where do we get the biomass? Sorry. So biomass is produced in the world at the scale of 100 billion tons per year. And less than 4% of the biomass is used, whether this is for food, ethanol, sweeteners, and so on and so forth. In the big biomass that we can use, the main compounds are carbohydrates, such as cellulose or chitin, chitosan. So this is really the majority of the biomass that we can play with. Then we have lignin that we heard of from the example of our colleague over here, which is a source of aromatic compounds, which constitutes almost a quarter of the biomass that we have here. And all the rest, proteins, lipids, terpenes, all sorts of molecules, it constitutes this thin sliver here, but it's been used actually a lot, especially lipids. So in fact, lipids is the largest chunk of biomass that we use in chemistry because it has some really more specialized application that we can tap onto. So another take on the renewables is also to take CO2 itself as a resource. So for instance, CO2 we know can be reduced into other molecules that can be used either as a fuel or as chemicals. This is an example of a technology that is developing that. So in this technology here, you're using a water electrolyzer to generate H2, and this H2 is then used in order to reduce the CO2 and create a synthetic fuel. So in this, the water electrolyzer is here. So you inject water, you will take H2, and then the H2 will be used directly to reduce CO2. And for instance, methanol that can be used as a synthetic fuel. So this is something that people are really trying to push right now to try to short circuit the biomass altogether and use CO2 as a resource. Lignocellulosics can be used actually for the bioethanol industries. So the cellulose can be transformed into bioethanol, and lignin powder is discarded or burned. Similarly, cellulose can be extracted to make paper. And again, lignin is discarded in this example. But lignin is really interesting. It's this really fascinating inhomogeneous polymer that has a lot of applications. In fact, I was told I shouldn't call it a polymer, I should call it a macromolecule because it's not polymeric in nature. There's no individual monomers. But you see, there's lots of diversity here, and also everywhere these aromatic cycles that are really important for making chemicals. So I don't have examples to show here, but you know that there is a lot of chemistry that is being developed for cleanly chopping off this material and make molecules of interest. And one of the examples is the chemistry that was discussed earlier of the Lutherbacher group in Switzerland. Other interesting molecules, chitin, we discussed it yesterday, so I'm not going to talk too much about it. Gelatin, we actually ate some several times since we arrived here. So you guys have this sorted. This is a protein-based material that, of course, is very well known for the food industry and is now being also developed for different chemistries. And finally, not everything's about polymers. So we have also been using terpenes. So terpenes are these class of small molecules that we can extract from nature. They have a lot of different applications. Usually they have very powerful scents that we could use in the perfume industry or the detergent industry. Some people are using them more and more as solvents and find them really interesting for that application. So you have different examples of people developing this. And this is an example from Unido, actually, I believe, right? That has been developed for, in the use of limonene as a solvent for different extraction processes. So this concept is really growing. This is a perspective on the bio-based economy in the US, and you can see that this is a rapidly growing market. This is one of the incentives probably for locals here in Indonesia to incentivize them in looking into this type of industry because it is really rapidly growing in a number of economies such as the US. It could be really a great economic opportunity for people in Indonesia to tap onto these types of molecules, especially these technologies are really rapidly evolving and developing. So again, what is important here is to consider in biomass the notion of competition with food, the notion of land use, the notion of preserving our forests and biodiversity. And while CO2 emissions may be reduced, other emissions are going up. So we know that when we use more biomass, we sometimes increase the use in fertilizers for growing the biomass. And that means that it's not true that biomass is going to be completely biomass is not universally better than petrochemicals, right? They're often associated with lower CO2 emissions, but even that you have to question and measure for sure. And they are, however, associated with more pollution through phosphorus and nitrogen release. So this is something to really take into account as you're making this move. So again, renewable feedstock, we're going to close on that, have an effect on a bunch of other green principles, such as the design for degradation. Often molecules made from biomass tend to be more degradable. Design for accident prevention, often these molecules are safer. They prevent pollution and they lead to safer chemicals, again, because we have molecules that are more compatible with biology because they come from nature to begin with. So I will close on this one because I think I'm running out of time. I have, we'll see how we're going to figure out the rest of the content, but I really want to have some questions from you guys if you want to ask them. Thank you so much for your attention.
Thank you, Audrey. Okay, so again, because a member of time, maybe 3 questions for this session, please. Anyone? Yeah,
Here.
go ahead.
Hello, Professor Audrey. Thank you for the opportunity. My name is Manda Edi. I'm from Indonesian Oil Palm Research Institute of Post-Harvest Research Group.
Okay.
Interesting presentation from you. Interestingly, during my undergraduate, I work on organometallic complexes based on palladium and ruthenium. It interests me a lot of what you have said, and also we are also working on deep eutectic solvents based on choline chloride and glycerol to extract phytonutrients from palm oil. However, like you mentioned in your presentation, is a non-volatile solvent. It is the main challenge that we are facing now. So do you have any recommendation, advice, or anything in order to replace hexane, because we use hexane a lot in the extraction, so we need to replace it with gas for now. So if you have any recommendation for that, you can give us some recommendation.
It's a very good question. Thanks a lot for asking. So you know that DES can be used for the extraction, right? But your problem is how do you get it out of DES after the fact? Am I correct?
Yes.
Okay. I don't really, I mean, there's been a number of papers on extraction with DES, and I can't remember how they take it out afterwards.
Some paper just mentioned another recovery of the DES with another organic solvent.
Yeah, exactly.
And it's nonsense for us.
It defeats the purpose entirely. I agree with you.
Yeah.
One thing that I've seen is that you can look maybe at the solvent guides and look if there is another solvent that would be greener than hexane, because hexane is toxic, right? But nonetheless perform in a similar in particular so the Green Chemistry Institute, they have a fantastic website. It's the same website as the one you showed, right? Yeah, so the site that is called Chemistry for Sustainability. Yeah, so the site called chemistryforsustainability.org contains a lot of tools, including solvent guides that are, so I showed you one solvent guide here, but in fact, you have an entire database of solvent guides that have been developed by multiple pharma companies. And this particular tool gathers a lot of that knowledge into one single place where you can check and see if you can find another alternative, greener organic solvent that would still be volatile enough that you can do your extraction at the end, evaporation and recovery at the end. From the top of my head for hexanes, I can't remember, but you can have a look at that. And I think that there are some solutions for hexane replacement. Yes, you want to?
I can say something. I would also argue that when you plan your synthesis and you're trying to use ionic liquids are especially interesting for the generation of products that are volatile, because that makes the workup really easy, right? Because you just heat it up a little bit and your product will come out and then you can use it again. So it's sort of, if you have a non-volatile product, I would say use the solvent guides, try to move into a greener solvent for extraction. Maybe instead of hexane, you can use some ethyl acetate or another acetate, something like that. But that the strength for ionic liquids lie especially in reactions that generate volatile products itself, because the non-volatility of the ionic liquid as
Yeah, I completely agree. But I mean, in this case, I mean, because this is an extraction from a natural resource, and you don't, as you lose the properties of the nutrients, I think you're stuck. And I think looking at the solvent guide will be chemistryforsustainability.org.
Or you could maybe also play around with the temperature, like lower the temperature and use vacuum so that you could remove a volatile compound at a lower temperature and with reduced pressure. So I don't know, that there might be some screws to turn on to. Tocqueville. Oh, okay.
Yeah.
It's a big molecule.
Yeah. It's a big molecule. So I think that we can have a look at this if you want. But yeah, I think a solvent guide is a good solution for you. Thanks a lot for asking.
Sorry, Professor. Actually, I have
go
another
ahead.
question.
Go ahead.
I'm very interested with your mechanochemistry also as well. My question is it also possible to do the mechanochemistry with one reagent is solid state and another reagent is liquid?
Yeah.
Or and also how how do you maintain how do you prevent the agglomeration during the reaction? Thank you.
Yeah, so that's two very good questions. Thank you so much. So what matters in mechanochemistry is that your mixture needs to be solid or paste. If it is slurry, then it stops working. So you can play with the liquid a little bit, and depending on the proportion of your different reagents, you may be able to maintain a mechanochemical while still having one of the reagent being liquid. So you need to check. This question of agglomeration is very interesting. So when things happen in really the solid state, in the powder form, you have this mechanism that I mentioned with comminution and then comminution mixing and reactivity at the interface. But a number of mechanochemical transformations happen more in the paste environment, where I believe that in this case, we have more a continuous solid phase that is more fluid than just a grain of powder. So I think in this case, the agglomeration is not really an issue. You work in a continuous solid phase environment where reagents diffuse in the solid phase. When you do mechanochemistry with grains, what we think is happening is that reagents diffuse in the interface between them. And this is often why having a little bit of liquid additive that we think absorbs on these grains help with this diffusion. So yeah, I didn't explain all of these details. Obviously, understanding that we are developing of mechanochemistry as a community, right? We have a number of conferences together where we discuss these things, and it's the things that you start to hear more and more from people that this is how it works. So yeah, you can definitely do mechanochemical reactions between a solid and a liquid, but it depends on the conditions.
Thanks a lot, Professor.
Very welcome. Thank you so much for your questions.
Terima kasih, Pak. Ada lagi pertanyaan? Mungkin? One more question?
Some more questions
Yes.
on catalysis, on solvents over here. Yes.
Thank you, Professor, for a very interesting presentation. My name is Oktia. I'm researcher at National Research and Innovation Agency. Currently, I'm working and have immense interest in the battery recycling using cathode recycling,
Okay.
using organic acids. At first, I was very confident that my procedure was environmentally friendly,
Yeah.
green,
yeah.
and then, because I use organic acids. However, after I tried working on it, I realized that I use more water than when than the conventional one, because conventional process use like inorganic strong acids, right? It doesn't require a larger amount of water. So what do you think? Which one do you think is better? When we compare the waste, the water waste like that.
Yeah, that's a really great point. So it's a difficult situation, right? Because indeed you will. So I also think you need to look into the water treatment that you need to do at the end, because it may be possible that from organic acid, the extraction of the organic acid, so you will form an organic salt, an organic acid salt at the end, right? You form the carboxylate of your so you may be able to extract them more easily than some of the salts that you form from the mineral acids when you use mineral acids. So I think the way I would look into is try to integrate the recovery and the cleanup of the water to your system entirely and see if you have benefits in using your organic acid by extracting it or reusing it, or potentially even I don't know what is the battery system that you're looking at. Is it a lithium battery?
Yes, lithium battery.
Okay.
So we extract nickel, cobalt, and manganese like that.
Okay.
So we use organic acids. Yeah.
Yeah, because some of the I don't know specifically your process, but usually organic acids are useful because they can chelate the metal and be better at extracting the metals.
Yeah.
So you need to compare the whole thing, right? What's your efficiency in metal recovery? Are you able to recover the organic acids eventually and reuse them? And what's the difference between those acids and minerals? I would not just focus solely on the quantity of water, because I think you have a system that's much more complex than that. And I would not drop the ball on it as well, right? But we need to measure things a little bit more closely. So compare the yields of recovery, and look at the recovery of the salts as well that you generate.
Okay, thank you.
if that makes sense.
Yes, thank you very much. I have one more question. if
Yeah, go
it's
ahead.
okay. Yeah.
Absolutely.
Regarding mechanochemistry, I mean, I'm interested in your procedure.
Mhm.
You said that the reagent should be dry, right? How to use reagent if it is hygroscopic? Uh-huh. Some what can I say? Some organic acids. It's like
Very
hygroscopic.
hygroscopic.
Yeah.
Actually, it helps because what
It
we
helps.
do is we mix the organic acid and it will trap water, and this water helps the reaction proceed. So small quantities of liquid can be very beneficial in mechanochemical setup. So for this reason, we don't see the hygroscopicity of the reagents to be a limitation. And I think I would actually love to try to see if mechanochemistry could work for your organic acid extraction, because
Yes.
I really think it should be very nice, and it might help as well with the water problem in your case. So reducing it and then providing a better way to recover at the end your metals and your organic acids as well.
Yeah. I really want to try that method for
Yeah, we
better
should. I
recycling.
mean,
Yeah.
we should definitely talk more and see
Yeah.
if this is something we would love to work on that. Absolutely.
I would love to talk more about that with you.
Sure, with pleasure.
The last question, sorry. uh, when you are going to scaling up, will you need higher force or longer time to do that, or just for you can use the same condition when you use the small ball mill?
Yeah, so this is not going to be an answer that can be generalized, right? We only try to scale one process so far. So I can tell you what happened with that one process, which is very special because it happens mostly by aging. So I think that helps with the scalability because the mechanochemical part is not too sensitive to how harsh the mechanochemistry is. So we've been able to scale our process using a simple food processor, which is very different from the ball mill, but for mixing our reagents, it seems to be working really in a very similar way. So the time, though, is a bit different because normally we mill for a few minutes in the lab, but it's not really feasible when you want to mill 10 kilograms, like mix 10 kilo, you cannot do it 5 minutes. Actually, you have to do it longer. So the time of milling is a bit expanded just because of the technical feasibility of what we're doing. The aging, though, is the same time. So the aging has been scaled so far completely linearly. We had to make some adjustment on the mechanochemistry part, but nothing too crazy so far. But yeah, we had to adapt to the fact we're working with a much larger quantity of material, essentially.
Okay, thank you very much.
Thank you so much.
Okay, there's like the use of enzymes by catalysts as well. Will it cost more money to run all the process? And what type of catalyst is more economical but efficient in terms of cost and environmental impact?
Okay, the
Very
first
condensed.
question, yeah.
What is the most crucial key in catalytic cycle?
Okay, the most crucial key in catalytic cycle. So when you design your catalytic cycle, you want to make sure that your catalyst goes fast in it and is recovered in full. So that you
So the time.
Yeah, so it's like you do your cycle fast, and also you recover your catalyst so you have high turnover number and high turnover frequencies. These are really the two main factors for good catalysis.
Okay.
For the enzymes, so we now see the price of enzymes have dropped dramatically. So there are more and more opportunities to use them in chemistry. My understanding is that the difficulty of implementing biocatalysis is with maintaining good conditions throughout the process and sustaining the catalyst throughout the process. So this is where biocatalysis is a bit still requires more work because the conditions in which it work are very sensitive. So the biocatalyst is going to be a little bit
Breakdown.
yeah.
Yeah.
What I'm hearing, I mean, I've been talking to companies who are doing biocatalysis. They're telling me now that the price of the enzymes has gone down a lot. So this idea that enzymes are expensive is no longer true. And you have a lot of enzymes that are super cheap. I mean, we have enzymes in all our detergent powders. You know, when every time you can think about it, every time you wash your clothes, you're doing biocatalysis, guys. There are enzymes in the powder that they're there to sort of eat the fat, and they're very cheap. Like otherwise, people wouldn't put them in detergent, right? So now we are developing more and more technology to translate that into chemistry. But again, I think my understanding is that it's maintaining the right set of conditions across the whole process, making sure that the enzymes keep surviving. That is the part that is difficult.
So to increase the cycle
Exactly.
of the catalyst.
Yeah.
Okay. And then the next one was how to make an ideal decision between catalyst selection and working capital.
Well, it's a bit difficult to answer because it's a very general question. I would say you need to give me more specifics. Some catalysts are very expensive, some catalysts are very cheap. So it really depends on the process. I think
it's not like one catalyst can fit for all situations.
Yeah. So you
depends on the
have,
reaction.
you have I try to explain here, there's a huge variety of catalysts that are adapted from extremely precise transformations in organic chemistry all the way to sort of zeolites that are making cracking in crude oil, which means handling 10 different types of reactions at the same time. And so it's really fascinating. I mean, you have a lot of very different things.
Okay. And the last one is in terms of cost and environmental impact, which catalyst is more economic and has lesser environmental impact?
Again, it really depends on the system.
Yeah.
In general, we try to go with so when catalysts contain a lot of heavy metal that can be toxic, and you can replace it by either a base metal or even non-metal catalyst, that will make it less toxic. So for instance, for pharma application, that could be a good development. But again, it's difficult to answer this question as a general. I think you have to look at your specific example. There are good solutions for a lot of different situations, and every time you have to compromise the cost, the greenness, and the performance of the catalyst. It's always the same things, right?
Yes.
So
okay. And then this is another question from Yudhistira. Does the ionic liquid can change organic solvent for organic pollutant separation like POPs or pesticide?
oh yeah, that's a good question. So again, this is for extraction from water, right? To the best of my knowledge, I think that people tend to look at solutions that are more based on a flow type of process. So rather having a solid state absorbent so that you can extract them from water. To my knowledge, I don't know that people are using ionic liquid that much for these types of extraction. It's also very difficult to do in a flow way. So when you do water treatment, you want to do it in flow as much as possible. You're not going to sort of mobilize a huge batch of water and then add ionic liquid to that. It's not really feasible usually to do it that way. So I am not sure ionic liquids are a good solution for POPs.
Okay.
Extraction from again, we're talking about POPs from mineral water, from municipal water, right?
It's saying like POPs or pesticide.
Yeah, but I'm assuming it's in water,
yeah.
that you know, so that you clean the water for.
So yeah, water treatment.
Yeah, water treatment. I'm assuming this is the context. To my knowledge, it's not very well adapted for that.
Okay. And then the last question is, do we need to consider also the grade of solvent, like pro-analysis grade or HPLC grade, etc., to change the solvent with ionic liquid? The grade of solvent.
I'm not sure it plays a big role. The grade of solvent is just the purity, right? So usually you use certain purity types because you want to make sure that when you extract, for instance, a chemical, you're not going to add additives to that can be bad or inefficient. Ionic liquids have their own degree of purities as well from the extraction, from the synthesis from their syntheses. So I would say probably you can use a comparable level of purity when you shift from one to the other.
So maybe not the grade, but like understanding the impact after using the solvent, and then analyzing what's the impact, what's the end results, and everything. Maybe like that. So because
yeah, so if you want to choose one of the, definitely studying the impact, studying using metrics to compare the two will be really important to make the right choice. Absolutely.
Okay, so that would be the last question for the session.
Thank you so much.
Thank you again, Prof. Audrey.
Have a good lunch.
Anyone would like to further discuss with Prof. Audrey, maybe during lunch, or maybe you should take a break first. But having lunch, with rice, and talking, right? So okay, so before we end this second session, maybe I'll just wrap up a little bit. Bear with me. I know you guys are hungry, So first is from the first session, what we knew before is different what we knew now. Before we were certain that hazard has flaws, there's toxicity. Saya Jaksel aja ya, saya gabung sama bahasa Indonesia mungkin ya. Jadi jadi dulu kan kita lihat ya kalau hazard itu ada kesalahan dalam suatu desain gitu ya. Terus juga polusi itu kita sangat optimistik bisa dihindari gitu ya. Terus juga kita juga sadari bahwa limbah itu juga belum dioptimalkan gitu pemanfaatannya, dan berbagai macam pemahaman lainnya gitu ya. Tapi dengan begitu kita juga intinya kembali ke diskusi kemarin bahwa kita harus tetap memenuhi functionality ya, kegunaan dari menghasilkan produk, tapi juga bagaimana cara upaya untuk bisa mereduksi hazard atau bahayanya. Sehingga harus ada holistic approach dari segi safety, performance, dan juga biayanya atau cost-nya. Dan mengacu pada buku yang diterbitkan tahun 98 itu sudah menjadi kerangka acuan untuk mendesain 12 principles in green chemistry. Tadi kita udah bahas dari waste and pollution prevention, strateginya bagaimana, lalu dari atom economy, lalu juga less hazard synthesis, bagaimana kita bisa memilih alternatif yang lebih aman, dan juga bagaimana kita menghasilkan produk. Tadi saya kalau tidak salah namanya, mohon maaf ya, phthalate ya. Phthalate are hormone disruptors tapi diganti dengan plasticizers if I'm not mistaken. And then the fifth is apakah kita butuh atau karena nyaman gitu ya. Jadi tadi ada auxiliary substances yang harus dihindari karena juga nanti efeknya tidak baik juga untuk lingkungan. Dan yang keenam, energi juga pasti berdampak terhadap biaya dan dampaknya juga terhadap lingkungan. Bagaimana kita bisa lebih efisien dalam memproduksi dalam proses tersebut. Dan juga terbarukan tentu adalah opsi yang lebih bagus daripada mengadakan barang yang akan habis dari sumber dayanya, dan mengurangi derivatif hal-hal yang tidak diperlukan dalam proses itu tersebut. Dan katalisator ini adalah suatu zat yang bisa mempercepat proses dan bisa harapannya kita bisa reuse, we can use the catalyzer again ya. Jadi kita juga harus kalkulasi berapa kali catalyzer ini bisa digunakan untuk proses yang sama. And then design for degradation, bagaimana kalau ada penumpukan satu jenis kimia tertentu pasti itu ada efeknya terhadap lingkungan dan itu harus direduksi gitu. Dan kita juga harus dalam prosesnya kita harus terus memonitor prevention pollution itu secara real time. Dan yang terakhir adalah kimia yang aman ini harus bisa menghindari kecelakaan yang mematikan. Kita sudah melihat kalau memang proses itu menghasilkan produk yang berbahaya, tentu itu harus dievaluasi gitu ya dalam pemrosesannya dan juga dalam penanganannya. Seperti itu. Dan sedikit dari sesi kedua, tadi ada 3 tipe katalis ya, ada biokatalis atau enzim, ada heterogeneous catalyst dan homogeneous katalis. Dan bahkan sudah ada studinya bahwa katalis itu sudah berkontribusi 35% terhadap global GDP. Jadi yay for the chemist, right? Dari katalisator ini bisa berkontribusi terhadap GDP. And then yang harus kita highlight tadi catalytic cycle itu lebih baik daripada stoichiometry regions. such as natrium borohydrate yang tadi dikasih contohnya, dan berbagai aplikasi gitu ya dari katalysator tadi, dan bagaimana kita harus menggantikan ya solvent-solvent yang tadi ada efeknya terhadap lingkungan, dan bagaimana kita mencari alternatif yang lebih baik untuk berbagai aplikasi dalam kehidupan kita. Mungkin itu saja summary yang bisa saya kumpulkan. Apabila ada kekurangan dalam penyampaian, saya mohon maaf sebelumnya, dan